So today we'll be reviewing conditional probability in tree diagrams. So the most important thing you need to know, of course, is the vocabulary. What is conditional probability? Conditional probability is the probability of an event A given that another event B has occurred already. And this is only for dependent events. So what are dependent events? Dependent events are events whose outcomes have affected or are affected by one another. There's also independent events, which doesn't really go with conditional probability, but independent events are those whose outcomes do not affect one another. And then of course, what's a tree diagram? Here's an example right here. It's a really great visual way if this is hard for you to grasp. Like for me, it's a really great, easy visual tool to use. It actually can be used for independent or dependent events. However, it doesn't really make sense to use it for independent events, but you can if you want to. So conditional probability, the most important thing to know is this formula right here. And the first part is read as P of the probability of A given B is equal to the probability of, this is both right here, both events, over the probability of your given event. And if A and B were independent events, the probability would just be the probability of A given B is equal to the probability of A, since they don't have an effect on one another. But if you just remember the probability of A given B is equal to the probability of both over the probability of your given, then you'll be more or less good to go. So here we'll do our first example. In a class of 30 students, 12 have dogs and 16 have cats. 6 students have no pets and 4 students have both cats and dogs. What is the probability that one randomly selected student has a dog? And so as you can see, it just says, it gives you the data right here. Really, conditional probability is pretty simple math, but it's just manipulating the statistics that you're given and being able to put that into an equation. And so your probability of, is there another marker or is this one's dying? Thank you. What? Yeah. My marker's dying. So your probability of having a dog is 12 over 30 students.
Try this one. That one works.
Thank you. Because right there we're just finding the probability that they have a dog, so that's an independent event because it has no, it's not affected by anything and it doesn't affect anything else. And so the second part of this example is, what is the probability that one randomly selected student has a dog given that he or she has a cat? And so it says right here, 4 students have both, so that'll be your, oops, sorry. Oh, D given C, that will be, if we use our formula right here, that will be both over your given, and it says right there, 4 students have both, so 4 out of 30, and probability that they have a cat is 16 out of 30, and you can cancel these 30s out, which is 4 over 16, and that is simplified to 1/4. And here's our second example. The probability that a randomly selected person has cancer is 0.02, and the probability that he or she reacts positively to a test which detects cancer is 0.95 if he or she has cancer, and 0.03 if he or she does not have cancer. Determine the probability that a randomly tested person reacts positively to the test. So first we have to find the probability of them reacting positively to the test if they have cancer, and that's going to be C times P, because they will be using C as positively having cancer and P as testing positively. And so that's going to be 0.02 times 0.95. And that's equal to 0.019. And then you have to find the probability that the person reacts positively to the test, but they don't have cancer. And so the probability of not having cancer, and we'll be using C prime to represent that, is 1 minus 0.03, and that's 0.97. And the probability of reacting positively, if he or she doesn't, is 0.3, or no, sorry. The probability that the person does not have cancer is 0.98. So you have 0.98 times 0.03, and that is equal to 0.0294. And so you have to add these two together, and you'll see this overlap with what we'll be doing with tree diagrams. And that ends up being, we add these together, plus 0.019 is equal to 0.0484. And we'll be using this information for the second part of the example. And the second part of the example is find the probability that a randomly tested person has cancer given that he or she reacts positively. And so you need to have your probability of both over the probability of the given. So the probability, like we found here, of them having cancer and having and testing positively to the test is 0.019, and the given, since this is both reacting positively, the given is reacting positively, and we found that here was 0.0484. And that simplifies to 0.393. So, erase this, and so now we're moving on to tree diagrams. They're pretty much used to illustrate sample spaces if the outcomes aren't too numerous. If you have a lot of different outcomes, you could be standing there all day drawing tree diagrams. But they are really great for, like I said, they're a really visual way to understand it. The most important thing you have to remember with tree diagrams is to multiply along these branches here. So if you're trying to find the probability of this and this, you have to multiply along this branch and then add down this final column of all your multiplication. So you can't add like here and here. You have to do your multiplication first. And if you can see right here, all these products end up totaling to 1. So our first example, our poor friend Carl here is not having too good luck with his car or his motorcycle. His car only starts 80% of the time, and his motorbike only starts 60% of the time. So we're going to draw a tree diagram to illustrate this situation and use the tree diagram to determine the chance that both vehicles will start. And we start by doing C and C prime. So C is for the car starting and C prime is for the car not starting. And then we have the motorbike starting and the motorbike not starting. So it says it only starts 80% of the time, so that'll be 0.8. And the other 1 minus 0.8 is 0.2. His motorbike only starts 60% of the time, so that's 0.6. And not starting is 0.4, and the same thing here. So if we wanted to find the probability that both vehicles will start, we have to look at this branch right here, since this is both vehicles starting, and 0.8 times 0.6 is equal to 0.48. And now we also have to find the probability that Carl can only use his car. So we are looking at C, the car starting with a motorbike not starting, and that is 0.8 times 0.4, which equals 0.32. And this is the final example. 60% of students in a class playing musical instruments are female, 20% of the females and 30% of the males play violin. Draw a tree diagram to find the probability that a randomly selected student is male and doesn't play the violin. So we'll be using M and F to represent male and female, and V and V prime to represent playing the violin and not playing the violin. So we have females here and males here, and 6% of the class is female. So 1 minus 0.6 is 0.4, and then V to represent playing violin and V prime to represent playing an instrument other than violin, and the same thing here. 20% of the females play the violin, and that would be 0.8 for not playing the violin, and 0.3. 1 minus 0.3 is 0.7. So if we're finding the probability that the student is male and doesn't play the violin, we have to look at M times V prime, and that's 0.4 times 0.78, which is 0.28. And the second part is the probability that a randomly selected student plays the violin. So this is going to show you how to add along this column down here. So you have to find the probability of them playing violin. And so 0.6 times 0.2 is equal to 0.12. And male and playing the violin is also equal to 0.12. 0.12 plus 0.12 is equal to 0.24. So that's going to be your overall probability that a randomly selected student in the class plays violin. So the most important things to remember about conditional probability and tree diagrams, if A and B are dependent, the probability of A given B is equal to the probability of both over the probability of given. And for tree diagrams, just remember to multiply along the branches and add down the columns if you need to, if you have to find different variables. So if anybody has any questions, that's the time.
Explain everything.
Thanks.